Hello, I'd like to present our recent project on uncovering task clusters in multitask reinforcement learning. This is joint work with Kate Rakelli and Somdeep Majumdar. In many practical applications of reinforcement learning, we would like an agent to solve multiple tasks. For instance, if we deploy a robot in a warehouse, we might want it to pack and unpack boxes, lift objects, turn in screws, and perform other functions. We'd like to solve all these tasks with high performance while also maximizing sample efficiency. In this work, we propose a method for multitask RL that parameterizes an agent as an ensemble of neural networks and uses a heuristic procedure to allocate tasks between the networks. By doing so, we improve performance and sample efficiency over a standard RL algorithm, soft actor critic. We also show that our method provides additional gains over an algorithm customized for multitask RL, PCGRAD. How should we design an RL agent to solve a set of tasks? Consider two alternatives. First, suppose we train an individual network to solve each task. While we may be able to obtain high task performance by using the latest RL algorithms, our learning process will be unnecessarily slow if the tasks are related. Rather than learning shared structure just once, each of our networks will have to acquire it independently. Now consider an alternative strategy, using a single network to represent all the task policies. In theory, this should provide us with improved sample efficiency by taking advantage of the shared structure. However, prior work has observed that this setup can be difficult to optimize, as learning signals from different tasks may be in conflict. We refer to this phenomenon as task interference. This may result in lower performance and slower training and practice. We propose a third alternative. We use a small ensemble of networks and divide the tasks between them. This method has the sample efficiency advantages of the single network approach, while avoiding optimization difficulties by separating incompatible tasks. In this work, we establish that such a method is viable by constructing task clusters from a dataset of training results. Our approach has 4 steps. First, we build a dataset of results using agents trained in pairs of tasks. This allows us to capture the effective task interference between each pair, and therefore helps us build larger clusters with least interference. Second, we use our pairwise dataset to estimate the performance of larger clusters. Third, using this estimated performance score, we search over clusters to find the best task assignment. Fourth and finally, we train a neural network to solve each cluster. By training agents in pairs of tasks in the first step, we can observe the importance of carefully selecting which agents are trained together. On the right, we plot the performance of the trained agents in a test task, peg insertion side. The two training agents are shown in the axes, while the color in the plot indicates the performance in the test task. For instance, the top right cell shows the performance of an agent trained in reach and window close when evaluated in peg insertion side. By looking at the row for peg insertion side and the column for drawer open, we can see that those two tasks exhibit task interference and would probably benefit from being trained separately. We now use the pairwise results to estimate the performance of larger clusters. We estimate the performance of an agent trained on a cluster PL on task I, which is in the cluster, as the minimum pairwise result consisting of task I and one other task in the cluster. Thus, our score captures the effects of negative interference between pairs of tasks, while ignoring higher order effects. We use the score to propose an optimal clustering of tasks, shown on the right. The clustering found by the procedure is not always intuitive. For instance, drawer open and drawer close are placed in different clusters despite involving the same object. Therefore, it may be important to derive clusters algorithmically, rather than relying on prior knowledge. We now train an ensemble of neural networks, using one for each cluster. In order to train a per-cluster policy, we use either SAC or PCGRAD. We compare our method against single network SAC, single network PCGRAD, and an ensemble of per-task SAC networks. We find that incorporating clustering yields improvements over the baseline algorithm. In the plot, the red curve indicating SAC with clustering outperforms the baseline SAC curve in blue. Similarly, PCGRAD with clustering outperforms PCGRAD with a single network for all tasks. Training per-task networks independently, shown in yellow, is able to achieve high task performance, but takes much longer. The combination of PCGRAD with our clustering method achieves the best results. Thus, our work has shown the potential utility of separating tasks in multitask RL. However, learning such a task clustering in an online manner remains a challenging problem. In future work, we plan to address this question by jointly learning an ensemble and a task assignment. Thank you.